Hi, my name is Zanzat, and I would like to present to you our paper about visual serving of cable-driven parallel robots with tension management. So, cable-driven parallel robots, or CDPRs, are parallel robots with cables instead of rigid links, and up to 6 degrees of freedom can be controlled by cables. Here you can see ICRA, which is our small CDPR. Its workspace is roughly 1 meter cubed, and its moving platform has 6 degrees of freedom controlled by 8 cables. The advantages of CDPRs are numerous. For example, large translational workspace, great scalability, low mass and motion, reconfigurability, and portability, which is not surprising that we can see many interesting applications for CDPRs. For example, here you can see a SkyCam, which gives immersive views of sports games, or for example, here we see the CDPR used for virtual reality applications. Of course, there are some drawbacks for CDPRs, and one of the main ones is the lack of accuracy. It's possible to deal with this drawback with visual serving. This is because in visual serving, we have a target that is observed, and the task is finished only when a desired accuracy is achieved with respect to the target. In our previous work, we have shown that CDPRs with visual serving control have high accuracy and high robustness to different perturbations in the system. However, cable tensions are not managed by visual serving, and this is not the task of visual serving. So it's possible that cable slackness can occur. And in the worst case, that can lead to the under-actuation of the moving platform and the loss of stability for the control. We propose a tension correction algorithm, which is a simple algorithm that compares the measured tension to a threshold, rapidly reduces even a large cable slack, and does not interfere with the main visual serving controller. Here you can see the main parts of a CDPR. So we have a base, we have the moving platform that has a camera on board and an object somewhere in the workspace. And here you can see the control scheme for the visual serving of a CDPR, with the main components being the visual feature vector that is computed from the image coming from the camera, the desired visual feature vector, and the error that is computed as the difference between the current and the desired visual features. The camera velocity can then be computed. Note that here we have the interaction matrix, which is computed in the following way using this formula. Now, from that, we can express the moving platform velocity by using the adjoint matrix. And finally, we get cable velocities by using the Jacobian matrix expressed in the moving platform frame. Now, cable slackness can occur for many reasons. For example, CDPR modeling errors, coarse estimation of the initial moving platform pose, cable elasticity and creep, coiling errors, having more cables than moving platform degrees of freedom. And the effects are the following. It acts as an additional perturbation for the control, and it's also possible that cable velocity does not produce the expected moving platform displacement. That can be shown in a very simple example. Here we have the moving platform with just one cable, and if we apply a velocity to this one cable, after some time, the moving platform moves. However, if we have slack in this one cable, and we apply the same velocity for the same amount of time, after this time, it's possible that the moving platform has not moved at all. To deal with that, we propose the use of tension correction algorithm, or TCA. And here you can see the control scheme with TCA inside that is shown in red right here. And now the biggest difference is the fact that now we have a velocity correction that is added to the control output of the visual serving. And this velocity correction is computed in the following way, where the main components are the tension threshold, the measured tensions, and the constant positive gain. Note that for us, in our modeling, the negative velocity means that we are pulling on the moving platform, so the cable is becoming shorter. And so if we add a velocity correction to a negative cable velocity, it means that the sum of these velocities is going to be larger, so the reduction of cable length is going to be faster. However, if we have a positive cable velocity and we add a cable velocity correction to this positive cable velocity, then the final cable velocity that's given to the robot is going to be smaller, so the increase of cable length is going to be slower. Here you can see the experiments. The very first experiment was done to validate the fact that with tension management, if there is no slack, the behavior is exactly the same as with classical visual serving. So the expected behavior was to have straight line here and straight line here, which is exactly what we get for both the classical visual serving and the one with TCA. Then we did experiments with 4 centimeter slack on 2 cables, which led to a deviation for the classical visual serving in the image that you can see right here. However, the TCA managed to reduce this slack, so the trajectory in the end was a straight line. And then we did another experiment with 8 centimeter slack, which led to an even larger deviation here for the classical visual serving, while TCA managed to reduce the slack in time, so we see no deviation in the image, nor of course in the 3D. Finally, just to show you the difference in moving platform stiffness when there is 8 centimeter slack, so classical visual serving on top, and the one with tension management. As you can see, by the middle of the trajectory, the tension management has dealt with cable slack and the moving platform is stiff, while the classical visual serving does not deal with cable slack and the moving platform was swaying. As I said, we added a cable slack on 2 cables. It was cable 1 and cable 2. And here you can see the length of cable 2 for the different experiments. And as you can see, there are 3 different lengths: the nominal one, the one with 4 centimeter slack, and the one with 8 centimeter slack. The slack can also be seen in a way in tension measurements, because we have only 2 experiments where the tension was above the threshold, and all the other ones have the tension at 0 newtons. And as you can see here in the velocity curves, there are 2 experiments where the velocity was increased. This is because the TCA was working on reducing the 4 and 8 centimeter slack. And what is interesting to note is that the moment here the brown and cyan curves go above the 1 Newton threshold is exactly the moment where here the increased velocity disappears and the TCA is no longer correcting anything. As our trajectory was diagonal, that you can see here, if there is any slack remaining, it's going to be on cable 5 and cable 6, which is exactly the case. As you can see here in the figure for the length of cable 6, there are 2 experiments with increased cable length, which corresponds to the classical visual serving without TCA with 4 and 8 cable with 4 and 8 centimeters of cable slack at the beginning of the task. And that can also be seen here as the 2 tensions go below the threshold. Now in the video you saw the April task trajectory, which can also be seen here, and the corresponding deviation from the ideal straight line trajectory. On the right part of the slide you can see the number of cables in tension and the stability of the system. Now it's interesting to note that the moment we have less than 6 cables in tension, the stability of the system is no longer ensured, and that corresponds to the moment right before the deviation from the ideal trajectory of the April task. Which is also interesting to note is that we have here an oscillation between 5 and 6 cables in tension, which corresponds to a slight oscillation here in this figure, which means that the moving platform was swaying a little. And here we also have a oscillation between 5 and 6 cables in tension, which corresponds to a larger oscillation in this figure, which means the moving platform was swaying even more. We also did a second set of experiments with tracking a mobile robot. Now you can see the first lab where the classical visual serving and the one with TCA was tasked with following this mobile robot that you can see. And of course, in the first lab, there is almost no differences between the 2 behaviors. However, when we get to the last lab, in each of these experiments, which was lab 29 for classical visual serving and lab 700 for the one with tension management, the behavior is quite different. For classical visual serving, there was so much slack already in the system that it led to the task failure, while after 3 hours of work, the visual serving with TCA still behaved almost exactly as in the first labs. So we stopped the experiment as we saw no degradation of behavior. We also did an experiment on a larger CDPR to validate the controller. So the CDPR is called Karoka. As you can see, here is its size. And what is interesting to know that Karoka has steel cables that are heavy and elastic. And in this experiment, it is tasked again with following a mobile robot. And as you can see, the TCA is dealing quite nicely with keeping all of the cables in tension. And you can see a slight oscillation here on this side of the image, which comes from the mobile robot not quite being able to follow the line that was on the ground that you can see here in this part of the video. So conclusions. The slack can lead to moving platform under actuation. The TCA is simple but deals with slack efficiently while not perturbing the visual serving controller. The tension correction occurs only when a slack is detected, and it is stopped as soon as the tension rises above the threshold. Its rapidity depends on the tuning of the gain and the amount of slack on the cable. The use of TCA allows to keep the CDPR perfectly responsive to the control signal even over a long time period. And future work includes the validation of the proposed controller on a fully constrained CDPR. Thank you for your attention.